Hello again everyone, welcome back to ptet.chemistry channel. In this video, I will specifically cover nucleophilic substitution mechanism, which is to do with, let me get this line straight, okay, which is to do with Sn1 versus Sn2 reaction. What do we understand by them? Okay, so nucleophilic substitution reactions are divided into two major types. Well, at least in A-level chemistry, it's divided into two major types. Okay, there are other nucleophilic substitution reactions, other types as you go to more advanced chemistry in university. But anyway, to keep things simple in A-level, you have Sn1 and Sn2. So that means it's nucleophilic substitution first order, or you can think about it the other way around, first order nucleophilic substitution or second order nucleophilic substitution reaction. Okay, what do I mean by first order and second order? Unless you have done A2 level chemistry on rate of reaction, you would not be able to pick up on this idea of first order and second order. Okay, so what do we mean by first order? That means the rate equation is just rate equal to the rate constant multiplied by the concentration of the, what I say, tertiary halogenal alkane. And I'll come back to it as for how we come to that as a matter of fact, yeah. So these are rate equations. They're actually determined by experiments, and all the theory you're learning in chemistry, they all come from experiment. So rate equation was determined from experimental techniques, which you will cover in A2 rate of reaction, right? So this is going to be the primary halogenal alkane. Well, I say primary, but it could just be a halogenal alkane. And when you have something in between, like secondary halogenal alkane, by right it could be either, and it has to come down to experimental observations as for whether it follows Sn1 or Sn2. So this idea of tertiary and primary is quite extreme, and when you are somewhere in between, it's quite hard to justify without doing the experiment and finding out whether it follows this rate equation or it follows this one, where there has to be two things in the rate equation, the other one being the nucleophile. Okay, whatever nucleophile you use. The square bracket refers to concentration, so rate constant multiplied by the concentration of that. These are to the power of 1. Okay, so there are two species involved in the rate determining step. So the rate determining step is the slowest step in the overall reaction, whereas here there's only one species involved in the rate determining step. If you have done A2 rate of reaction, you would know the definition of rate determining step is that it's the slowest step in the overall reaction. Any reactants that are involved in the rate determining step would appear in the rate equation. On the rate equation, you will get the total order of reaction. Here there's just one reactant here to the power 1. That's why it's just first order overall. Here there's 1 and 1. Altogether, there are two reactants involved in the slowest step of the reaction. It's a second order overall reaction. So what do we actually mean? So if you're an AS level student, realistically speaking, you are just here for the mechanism, okay? So let's walk you through the mechanism and think about it, okay? Because they're important as you go to A2 as well, upper 6, where there will be more stuff that links together with rate of reaction. Okay, my lines are really bad there, so you gotta pardon me on drawing a straight line. I'm not always been very good at drawing straight line, okay? Anyway, we said that it involved tertiary halogenal alkane, and why is that? Because when you go via Sn1 here, okay, we proceed via a carbocation intermediate. So it's via a carbocation intermediate, whereas an Sn2 proceed via a transition state. What's the difference between intermediate and transition state? Well, that would have been covered in your chemical energetics topic. That is from your AS topic. That is on chemical changes. Well, energy changes, chemical changes, energy changes. Yeah. Okay. There will have been definition of intermediate being a species which is more long-lived and you can isolate it, whereas transition state is very short-lived, very high energy, and you can't isolate it at all. It's just it's just assumed to be there. It's like the most reactive part of a reaction, yeah? Okay, it's a reactive species. Whereas carbocation is reactive, but not as reactive as that. You could isolate this, you cannot isolate that, all right? So when you have a Sn1 mechanism, it proceeds via a carbocation intermediate. So straight away it tells you is two-step. It's two-step. Transition state, it's one step. Okay? Everything in one step. Alright? I know it seems counterintuitive. The Sn1 does not refer to one step. The Sn1 refers to first order, which is only one substance in the rate determining step. Okay? So you gotta be careful what the Sn1 and Sn2 refer to, yeah? So because they are two-step, and I know it because they proceed via carbocation intermediate, I will try and exemplify it. Or maybe I should write an overall equation. Example, overall equation. Let's choose a tertiary halogenal alkane, CH3, CH3, CH3. Let's choose a Br, because Br is nice and weak there compared to CCl, I guess. Let's choose NaOH. So what will we get? This is an overall equation. So an overall equation is not a mechanism. It's just showing you what will happen. Okay. So this is specifically called hydrolysis because you are using the OH minus to attack the C there to substitute the Br with OH. This is specifically called hydrolysis, but it's actually a type of nucleophilic substitution reaction. So you have been alright unless they ask you to name the specific type of reaction. Yeah. We are also going to do hydrolysis here, but we are going to use CH3, CH2, Br. Why do I write that? I want an overall equation, so I can just use a structural formula. CH2Br plus NaOH. You could use KOH as well. I mean, it will work similarly as long as it's a source of hydroxide. And then you just replace the Br with that and that. These are overall equations. There's no way to tell whether it's one step or two step. There's no way to tell whether it's first order or second order because we are not doing mechanism there. So when they ask you for mechanism, so pardon me for writing that as mechanism. Perhaps I could just rub that out. Okay, so now I can draw the proper mechanism. Okay, so based on what I said earlier about all that, about like the rate determining step, the intermediate for Sn1. Okay, so there are two steps to it. So first of all, you will have your tertiary halogenal alkane. By the way, why do we say that this is a tertiary halogenal alkane? Because the carbon bonded to the halogen is bonded to 1, 2, 3 other carbon. That's how you identify this as tertiary halogenal alkane. The carbon bonded to the halogen is bonded to 1, 2, and 3 other carbon. It's a tertiary halogenal alkane. The carbon bonded to the halogen is only bonded to one carbon. You can draw out the display, which I'll do in my mechanism, and hopefully I'll remind you again later on. But you should be aware of this thing. Yeah? This bond is polar. Okay, these are CH3 group. This bond is polar. These are considered non-polar group, hydrocarbon, right? On its own, it will just break like that. This is slow. That's why this is the rate determining step. Rate determining step. I talked about it earlier. Okay, there's only one species involved in the rate determining step. It's the slowest step. It's the halogenal alkane. The halogenal alkane is involved in the slow step. There's only one species here. There's nothing else to make it break. It just breaks like that. And what would you get? You would get a carbocation intermediate. But don't forget, your equation needs to be balanced like that. And your bromine will have the 2 electrons because of the hydrolytic fission. Okay, so that equation is balanced. And your step 2 will involve your halogenal alkane, sorry, not your halogenal alkane, your carbocation intermediate being attacked by the hydroxide. Technically speaking, this one can also compete with this because this has lone pair of electrons, so it can also be nucleophilic. But you want to form the ultimate product where the OH replaces the Br, right? So we're just going to concentrate on the lone pair from the nucleophile attacks the carbon. I have drawn that really badly there, so I'll redraw that again. maybe I can put the charge there. Doesn't matter where you put the charge, right? As long as it's on the carbon. Okay, I want to show from the lone pair which is rich in electron, attack the carbon. It's not from negative to positive. Yes, negative ions are attracted to positive ions, but which one are the bond being formed? Mechanism shows the movement of electrons from the rich in electrons, from the to the poor in electrons. Okay, it will form the bond that you will form. You will form a CO bond. You will form CO bond. Okay, so actually you need to show to the carbon itself. Yeah, it's not H now. It's CH3. CH3, CH3, OH. Okay, the Br minus was already there, so I won't write the Br minus because they are not involved in this second part of the reaction. This is the fast step. Okay, maybe I can move it a little bit to the right to make it look better. This is the fast step because recombination of ions. You are not breaking anything, you are just forming bond. You are breaking something, you are not forming something. Slow, fast. I hope you can see that. Okay. Alright, so because this is a slow step, only one reactant appears in the red determining step then, okay? It's just the halogenal alkane itself. That's why it's just the red constant multiplied by the concentration of the halogenal alkane, alright? Next question really is, why does tertiary halogenal alkane prefer this route? As for why primary halogenal alkane prefer the Sn2 route? Well, let me draw the mechanism for an Sn2 reaction. For this particular example which I have chosen, which is bromoethane. Of course, it could be any primary halogenal alkane example really, but I've just shown you using that. It's a primary halogenal alkane because the carbon bonded to the halogen is bonded to one other carbon only. I probably shouldn't write the C like that because the carbon is bonded to the carbon. Structural formula is okay, but when I draw display, the carbon is actually bonded to the carbon is not bonded to the hydrogen there, okay? The dipoles, as usual, I know it's one step and it proceeds via a transition step, which I'll talk about later on. Do you see this thing here? This is called a carbocation intermediate. I should really put a label somewhere, carbocation intermediate, but I ran out of space here. You should really write down carbocation intermediate, all right? So what happened in that one step is that the hydroxide, which is the nucleophile, that means you have to show a lone pair on the nucleophile attacking the electron deficient carbon, electrophile, nucleophile, rich in electron density, poor in electron density. Attack from the rich to the poor, you are not forming the bond from negative to positive, you are forming the bond between oxygen and carbon, So you need to attack from the oxygen lone pair to the carbon, and then you will break the CBr all in the same step, okay? I'm going to draw the transition state because that is very important, okay? The transition state. How would the transition state look like? Running out of space here though. Better draw it properly. This is your incoming nucleophile. This is your outgoing CBr. This is a transition state. The carbon is as if it has 5 bonds, but it does not because this is a very reactive state. This is called transition state. It has a negative charge simply because no charge plus negative charge, you have a negative charge. We have to write it as this thing. I don't know what this symbol is called, but it's like a double line and then it's a dagger. We call it a double dagger. Yeah, double dagger. Okay, it's to show it as a transition state. In a bit of time, in a moment, I'll show you what I mean by transition state. But carbon don't usually form 5 bonds, and it's not exactly 5 bonds. These are like partial bonds. The incoming nucleophile, this bond will slowly get formed. So this bond will get shorter, and this bond is the one that's been broken. So it will get longer and longer. As this gets shorter, this is the new bond being formed. This old bond will get longer and then it breaks. There is nothing for this to be involved in a reaction. They just sit there very happily. This is coming out towards you. This is going in away from you into the screen or into the paper. These are flat in the screen or in the plane of the paper itself. Yeah. Anyway, so you don't isolate the transition state, and then what happened is I've already shown the electrons flow in one step. That's all I need to do. I show this. I do not show the bromide being broken here anymore. This is just whatever is occurring as this process is happening. Yeah. So what I will get is I will get that, and then I'll get Br leaving like that. A lot of people, they will get the product, but then they forget about the other thing that leave. Just like in your electrophilic addition mechanism, in your nucleophilic addition, well, in any mechanism you draw, what has left? Okay, so you gotta show it. What has left, you gotta show it, all right? So what's the difference there? Transition state and an intermediate, okay? This is the idea that we're going to talk about right now. Let me get the line a bit straight. Sn1 and Sn2. We talk about intermediate, right? Therefore, we need to think about energy profile diagram. Okay, it's best represented by an energy profile diagram. We'll have energy and then progress of reaction. Where I have energy and then progress of reaction, or you can talk about extent of reaction, okay, or time as reaction progress over time. Okay, I'm assuming the reaction is exothermic. I know I have an intermediate, okay, so it will proceed via a slow first step and a fast second step. Slow first step, fast second step. Why is that? Well, you can look at the activation energy. Okay, the activation energy for the first step is a lot bigger than the second step. And why is that? You need to break the bond on your own. No bond being formed. Okay, it's slow. You are combining a cation and an anion. You are not breaking anything fast. All right. As for Sn2, because it's proceed via transition state, it's only one step. Everything happened in one step. Okay, we can call that concerted mechanism, meaning to say everything happened in one step, or one step mechanism, whichever word you like to use really. Reactant going to product. Reactants going to product. You are doing substitution, so you end up with, if you start with two things that reacted together in a substitution reaction, you end up with two things again. That's the idea of substitution. You are just substituting the Br with the OH. You start with two reacting molecule, you end up with two things here. You start with two things, you end up with two things. It's opposite, it's different, it's in contrast to an addition reaction where you join together, where you combine together, so you will get lesser than what you put in. But a substitution is not an addition. You get the same number of stuff as you put in. Okay, so what can I say here? Well, this reaction also has activation energy. Okay, I don't want to focus too much on the enthalpy change because I could be very wrong on the enthalpy change of the reaction. But the idea is that this will give you a double harm reaction profile diagram. It's not a symmetrical double harm because you know the first step and the second step have different energy requirement. One is going to be faster than the other. Okay, the slow step, this will appear in the red equation. So this thing here is what we call a carbocation intermediate for your Sn1. Sorry, my handwriting is a bit small. This thing there is called transition state. It is that thing there, the double dagger. Guess what? There's a transition state there and there's a transition state there. But it proceeds via intermediate, so we are not too concerned about what those two transition states are. But we are concerned about this because it doesn't proceed via an intermediate. So the transition state is everything we know about this. Okay? Now the question really is, why? Why does Sn1 favor tertiary halogenal alkane? Or you could think about, why does tertiary halogenal alkane like to undergo Sn1 and not Sn2? Okay, so there are two ways of looking at it. Why Sn1? There's one reason. Why not Sn2? There's another reason. Okay, let's think about it. All right, so we're gonna think of it in the context of the mechanism itself. All right, so why tertiary halogenal alkane prefer to undergo Sn1? There's one reason. Why not Sn2? Okay, I'll address the first reason first. Why Sn1? In your Sn1 mechanism, you need to form carbocation intermediate. I talk about stability of carbocation intermediate in my other video on electrophilic addition, part 2, that is on the, because we also get carbocation intermediate when we do electrophilic addition across alkene. So I suggest you to actually watch that video first before you proceed further. In fact, that should be the order, right? You should have covered electrophilic addition before you cover this, okay? So go and watch that video if you want to know more on in detail on how I explain the stability of carbocation intermediate. Essentially, what we are talking about is inductive effect. So these are all explained in detail in the other videos. Electrophilic addition part 2. So these are positively charged. This CH3 group are alkyl electron donating, okay? So I'm going to compare that with a secondary. I'm going to compare that with a primary. So here, okay, I've shown this arrow. What does this arrow mean? It means I have more alkyl group. Alkyl group can refer to methyl, such as CH3. It can refer to CH2, CH3, which is ethyl. 3-carbon alkyl would be propyl, butyl. You can get isomeric alkyl. They are all alkyl group. Okay, alkyl groups, which are electron donating. So these are the terms that I use in the other video as well. So they are electron donating, and they will stabilize the positive charge. It's very important that you get this term correct. Inductive effect, INDUCTIVE. Electron donating group inductive effect. Therefore, carbocation, which is positively charged, is more stabilized. Or you can say carbocation, tertiary carbocation, because the carbon with the positive charge is bonded to 1, 2, 3 other carbon. Okay, it's more stabilized than secondary, it's more stabilized than primary carbocation. If you can stabilize the carbocation even more, your intermediate is going to be lower in energy. So you can imagine if this is your tertiary carbocation, your secondary will be higher, your primary will be higher. So to go through via the primary, for primary halogen alkane, if it goes through Sn1, it will have a very high energy intermediate, which is not stabilized because you only got one alkyl electron donating group. It's not very stabilized, and therefore, I wouldn't really want to go through via Sn1. For tertiary, it's good because I have 3 alkyl groups, which can stabilize my electron donating group by inductive effect. If I can stabilize the positive charge, I get a much lower energy intermediate, which of course is still higher energy than the reactant and product, but the lower the energy of the intermediate, the more stable it is, okay? And therefore, it will more likely to proceed via an Sn1 mechanism, which is a 2-step mechanism as shown previously, yeah? Okay, why not Sn2? Okay, why not Sn2? I just said just now, right, why Sn2, why primary halogen alkane doesn't like to go Sn1 because of the stability of carbocation, okay? I'm going to relate that to here, okay? Well, not really. So I'm kind of all over the place now, but I hope you can see the relationship. If a tertiary halogen alkane, so maybe I should put a divide there. Okay, let's put a divider there. If tertiary halogen alkane proceed via Sn2, is that good or is that bad? All right, let's have a look at this thing. Just now we look at intermediate. We're going to look at the transition state if we have a tertiary halogen alkane. If we have a tertiary halogen alkane proceeding via Sn2, which it doesn't like to, yeah, then the transition state will be looking like this. Okay, so the dotted line for the partial bond. So you have a CH3, the CH3, and the CH3. Okay, negative charge. Is that good? You don't see it on paper because when you draw it on paper, you are forgetting one thing. You really forget one thing. Atoms occupy space. What you see on paper is not really what happened in reality. You need to think about the size. Carbon central is actually quite small, yeah? You already have this weird looking transition state, which is actually the top of the peak. It's already quite unstable. And now, if your tertiary halogen alkane actually proceed via it, the energy is going to be all the way up there, which means you're going to have so much high activation energy. Why is that? Why is the tertiary halogenal alkane, if they proceed via Sn2, why is their transition state so high in energy? Well, because they will repel. Look, alkyl and alkyl. If they proceed via that Sn2, okay, they are very steric repulsion, okay? This idea of bulky groups of alkyl, they can repel around this really constrained geometry. That's why you don't like, tertiary halogenal alkane does not like forming the transition state at all. That's why it's going to be all the way high up there in energy. Primary is going to be the lowest energy transition state, which again is more reactive than reactant and product, but that's the most favored pathway for a primary halogenal alkane to proceed, because nice and happy. This is nice and happy there on its own. This one is obviously on the opposite end, because as you form this bond is being broken. And these are hydrogen. They are a lot smaller. In fact, hydrogen is the smallest atom, right, you can get. All right, they're a lot smaller than alkyl and alkyl, which you don't see it. But remember, there are CH3. There's 3 hydrogen on each carbon there. So the whole idea comes down to tertiary halogenal alkane do not form very stable transition state. Okay, because there will be steric repulsion between the bulky alkyl group, whereas tertiary carbocation is nice and stabilized by this electron donating group due to inductive effect. Tertiary halogenal alkane prefer to undergo Sn1. For primary halogenal alkane, they don't have that problem of repulsion of the alkyl group in the transition state. So primary halogenal alkane can form transition state that is of lower energy compared to that of tertiary halogenal alkane. They will have repulsion between the R group, the alkyl group, if and when they form transition state. The other reason is, well, primary halogenal alkane do not form very stable carbocation, because here you only get one inductive effect from one alkyl group. Here you get 3 alkyl groups that can contribute to the inductive effect. So it's kind of like a rounded argument, but there are 2 sides to the argument, one of which is stability of the carbocation intermediate. The other one being the stability of the transition state, okay, as a result of the steric repulsion, okay. So this is to do with the orientation in space, this is to do with the space filling, this is to do with steric. This is to do with electronic density, this is to do with electronics. So 2 factors govern chemical structure and reactivity, one of which is electronic, which you are obviously accustomed to, because talk about nucleophile, attack electrophile, rich in electron density, attack poor in electron density. Steric, however, is not very well explained in A-level chemistry, but as you could see in this Sn1 versus Sn2 reaction, it does have a role to play for why the tertiary halogenal alkane do not typically undergo Sn2 reactions. In addition to the electronic reason, there's the steric reason as well. Okay, I hope that explains it, Sn1 and Sn2 comparison. So there's a lot of things covered in here. One of which is not actually in your AS syllabus until you cover rate of reactions, and then they love to combine the 2 together. All right. Yeah, so I hope you enjoyed this explanation, and if you do, please subscribe to the channel and share the channel so that more people, students and teachers or friends, can benefit from these videos. And I'll see you in the next tutorial video. Yeah, thank you for watching.